Hey, what's up, guys? Okay, so welcome to my algebraic geometry second video, affine skin second video. So in this video that I'm gonna to talk about example of affine skin, but basically only talking about set. And yeah, basically I think previously we already defined let's quickly say A is commutative ring with identity, and one can define a spec A, which is all the prime ideals of A. And you can define a vanishing F. Vanish, somebody give you the set S, subset of A. You can collect all the prime ideals which S belongs to P. And conversely, if somebody gives you and I define this V of S is all closed, this is defined to be the Zariski topology. And for D of F, then the one can define P, where this is prime ideal do not contains P. Do not contains F. Okay, so this is called distinguished open set. And in my previous video that I have showed that basically if you have F1, F2, Fn equals to A, then you can show that the D of Fi, the union of this D of I will be the spec A. Okay, so the distinguished open set will form the spectrum. And I think this is my I have one video that gives you the property of this distinguished open set. Okay, so and the next thing that I have not yet shown is that in the next video I will talk about structure sheaf. Okay, so if you add a structure sheaf, then you will make this skin to be a local ring space. Okay, so quickly say is the quickly way to say is that you can define a structure sheaf. Let's say O on the prime ideal, and let's say let's write a different way. Right, so spec A will be have a sheaf. Okay, and this sheaf of spec A apply on the apply on any D of F will be the localization AF, and the stocks. Right, there's a stocks, right? So stock at P will be just localized at P. Okay, and this is just a minus P localization on A, and this is just the multiplicative set of this. So 1F squared F dot 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 dot. Okay, so minus 1 and A. Okay, and in the third video that I will show, this guy really forms a structure sheaf by prove it satisfy the sheaf axiom. Okay, so all these are all the ingredients of the affine skin. So affine skin become a local ring space. Okay, but in this video I only talk about examples. So examples I will not talk about the property of structure sheaf, but I only talk about these two parts. Okay. So these are very simple examples about affine skins. So let's talk about maybe 10 examples. Okay, and you can follow, I think, the Google is follow the Cal 3.2. There are many examples. Okay, the first one that very simple is a affine line. Okay, so very simple. You can take the RA to be complex. The C of X, and our spec A will just be this is our affine skin spec C of X. Okay, and by definition, these guys so we ask the prime ideals of this, right? But this is so basically this is polynomial ring. So prime ideal of the polynomial ring is just the irreducible polynomial of C of X. Okay, and we know that by the fundamental theorem of algebra, like C is algebra closed. So basically, these all prime ideals are basically generated by X minus A. Okay, and there's a special ideal, it's 0. 0 is also a prime ideal. The reason is that the C of X is integral domain, right? So if you quotient 0, then you still get C of X. Sorry, so C of X is integral domain, right? So 0 ideal is a prime ideal. Also, you can imagine that this is a line. The reason is that imagine this is complex plane, and each point there's A. You can view this point, one point corresponding to one ideal. So this is X minus A. Okay, and yeah, so these are all the ideal. These are all the points. Okay, so this is a line, right? So it's amazing that if you ask the spectrum of C of X, then it's really a line. So this is a geometry interpretation of this affine scheme. Okay, and there's a fat point which is 0. Yeah, 0 means that, so you imagine that this point A, right? You can imagine it's a root of x minus a, right? But all the points are basically 0. All the points are basically can be used as a root of 0. So you can imagine that all these are, there's a fat point called 0. Okay. 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 So yeah, so yeah, this is like this is just a picture of this affine line. Another picture that you can imagine is that okay, yeah, I think this is the usual way to draw this. Okay, and some of like the people will draw the 0 to be at the infinity. So basically, you can draw a line at each point. Ideal and a 0 can be drawn maybe here. Okay, there's a 0 here. Well, this 0 has a special name. Okay, we will talk it in the future. Okay, and yeah, so basically, if you take any algebraic closed field, you can also define a spec K of X. Okay, so this is usually denoted AK1. Okay, so this is the example 2. Now let's consider example 3. So this one is very simple. If you ask a spec of Z, so basically the prime ideal of Z, so prime ideal of Z is just a prime number. Okay, so the multiple of prime, so prime number. And the Z is also a domain, right? So you can add 0. Okay, so one way to draw it is that you have 2 and the 3 and the 5 and the dot dot dot, and then maybe there's a 0 point here. Okay, and I have also want to say you can in this affine scheme language that you can view the function of you can view the element in the ring as a function. So this is why somebody like to write f. So f as a function on spec Z, or on a general A. Okay. Okay, so how to view how to for example, let's choose f to be 100. Okay, so in these 3 that I can just this root is just 1. Its answer will be very well be 1, right? So I just quotient 3. Okay, mod 3, and for this one is 0. Okay, 0. Okay, so basically one can view a function f one can view a function. One can view f as a function on the spectrum. Okay, for example, in this case that you can write, for example, you can write f(x squared) to x squared minus 3x plus 1, and you can ask what is its value on x minus 1 ideal. Then the answer will be very simple, just f of 1. Okay, so just 1 minus, yeah, so it's minus 1. Okay, so the function, the element of the ring can be viewed as a function on the scheme. Okay, and the general definition that we will talk in the future, but basically the idea is very simple. Is for these two examples, right? You can do this, and also you can define a so-called rational function. For example, in a spec Z, you can like 27 divided by 4, this kind of thing, right? As a rational function, you can view it as a rational function of spec Z. Okay. Okay, so I will make this definition in the future. Yeah. Okay. So this is another example 4 is very simple, and you can consider Okay, we can consider spec K, right? If you only take a K to be a algebraic closed field, then or Fourier field, spec K just only element 0, right? Because this is only prime ideal. Okay, so it's only 1 point. And there is an example that you can show, you can try to play around with is that if you take the spec K of epsilon and say quotient epsilon square. Okay, so as the prime ideal that we will, so this is a quotient ring, right? So the prime ideals corresponding to quotient ring is basically the prime ideal containing epsilon square. So this is the prime ideals in K of epsilon and but the prime ideal containing epsilon square. Okay, so I think this is not difficult. The only prime ideal which contains epsilon square is only epsilon, right? So this guy only has 1 point, which is generated by this epsilon. So so you can think that as a topological space, these two are the same. So they are homeomorphic to each other, right? Because they are all just 1 point topological space. So this point must be closed and open. So it's the same as spec K. Okay, but their sheaf are different. Or basically they are ring. They're basically their ring, right? Their rings are different. Okay, because these are different ring, right? Because this is not field. Okay, so it's basically not domain. Because you can take epsilon is non-zero and this is square defined to be 0. Okay, so yeah, now let's working on some other examples. And example 5, you can ask, for example, the ring to be the R of x, so it's a real number, and you can define a spec of real number of x. So I think everyone knows this. This is the irreducible polynomial in R. So it's either 0 or x minus a, where a is a complex, sorry, a is some real number, or basically the x squared plus ax plus b if there's no real roots. Okay, so yeah, this is the quadratic. Okay, and also everyone knows it. If you do the quotient, of this 0, then you get the same thing. If you get do the quotient of this x minus a, that simply speaking, you get a real number. If you get a quotient of any x squared plus ax plus b, then you are just adjoint the adjoint a complex number, so a complex I, right? So you can prove this isomorphic to C. Okay, so it said this guy can be used as a dimension 2. This is dimension 1. This is dimension 0. Okay, and there's an example that I will not do the detail, but you can also you can investigate this kind of thing. Basically, you can work in a finite field and ask the spectrum. Okay, so now let's let's say working example 7. You can do the affine plane. So basically, you take this. So you take the complex two variable complex coefficient complex polynomial and take spec. Then you can define AC squared. And this guy is basically a little bit tricky, right? So the points will be the irreducible polynomial. For example, we can draw irreducible point. So this guy is a f of xy, which is irreducible polynomial. And at the points that maybe there's some points, for example, x minus 1, probably x plus 1, 1 minus 2, these kind of points. Basically, it's minus 1, 2, these kind of points will correspond to this ideal is maximum ideal. So these points are maximum ideal. And the irreducible curve on it is prime ideal. Okay, so this guy is a prime ideal. And there is also a fat point which covers all this. There is a 0 point, which is generic point. Okay, so these 3 of them corresponding to the spec of CXY. Okay, now you can do in the more general, consider the spec of, let's say this is n, so spectrum of C of x1, x2, xn. Okay, so this is like the main object that one can study for a variety, right? If you quotient something, you get something. Okay. Okay, and in the next video that I think these are fundamental examples, right? But in the next video that I want to talk about the quotient and the localization of the spectrum, because I think these two should be viewed as a special one that completely different from these two simple observation. Then that will be hard for you to draw. So this is why I want to make a particular video for you to do. Like there are two special kind. One is the quotient, one is the localization. So we want to study the spectrum of a ring over 1 and 2. Okay. See you guys next video.